Hey, hello everybody. Um, the plan today for the supplemental recording is to just work through some additional examples on parametric equations. We introduced these ideas already, so we should have kind of an idea of the background behind what we're going to cover today. But we're just going to go through some extra examples for a little bit of extra practice. Okay, so the first example we're going to look at is a basic parametric equation where we want to eliminate the parameter and draw a graph. So the first thing that we might notice is that we have x and y are related to each other through theta, but through trig functions, through cosine and sine. So if we want to eliminate the parameter, if we want to get rid of the theta, we're probably going to be looking for something like a Pythagorean identity somewhere. So the sine squared is already kind of in the correct form. The cosine, I would like that to be squared. So I'm thinking that y is going to be somehow related to x squared, or in particular, y over 4 is going to be sine squared theta plus, and then x squared would be plus cos squared theta. And then I know this has to be 1 by the Pythagorean identity. So this has to be 1. Or I could say that y equals negative 4x squared plus 4. And then I could come down here and I could graph y versus x, and I see that I have a quadratic opening down. It goes through 0, 4. I see that it also goes through plus or minus 1, 0. And I might draw my quadratic like this. So we might think, okay, this is what y in terms of x looks like. But if you remember, we kind of mentioned before, we had to be a little bit careful when moving from the parametric world into the xy world, because we were interested in things like, for instance, as I progress through theta, as I let theta move through the real numbers, do I trace out this entire function? Do I trace it out from left to right or right to left? Maybe I'm interested in where on the graph is, say, theta equals 0. What point is that related to, and so on. So one thing that we might realize is that, well, x of theta is cos of theta. So x is actually stuck between negative 1 and 1. And y, for sine squared theta, we know sine squared theta is between 0 and 1. So y is going to be between 0 and 4. So we might want to be a little bit more careful with our graph in the xy plane. We know that it's actually not going to go forever to the left and the right. So we're going to kind of end here, and we're going to end there. But now we have kind of an interesting question, is that, well, theta can really be any real number. So what happens? Do I kind of crunch the whole real line down to just the small interval, or how does that work? Let's start by looking at, say, theta equals 0. Well, cos of 0 is 1, sine of 0 is 0. So I see that theta equals 0 is my rightmost endpoint here. For theta equals pi, we see that x is going to be negative 1, y is going to be 0. So I have theta equals pi over here. So I go from the right over to the left, seemingly from theta equals 0 to theta equals pi. Right? I know that cosine on 0 to pi, aka x on 0 to pi, is going to go from +1 to -1. It's not going to do anything crazy in between there. It's not going to jump back and forth a bunch of times or anything. So I'm going to have a nice traversal from the rightmost point of my curve to the leftmost point of my curve when I go from theta equals 0 to theta equals pi. Now, of course, everything is 2 pi periodic, so I could have also chosen to go, say, from theta equals 2 pi to 3 pi, something like that, right? So that would also traverse this curve in that same manner. What happens when theta goes from pi to 2 pi, though? Well, theta equals pi, we know, is over here, and theta equals 2 pi is over there. So we've got to get back from the left to the right somehow. And of course, we are just going to come back this way for theta going from pi to 2 pi. So we see really what's happening as theta goes from, say, 0 out to infinity, we're bouncing back and forth from the right side to the left side to the right side to the left side. Let's see if we can get that behavior to show up on the calculator. So again, I'm going to go into mode, make sure I'm in the radian mode, and make sure that I'm in the parametric equation mode as well. When I go to y equals, I should see my parametric equation mode where I have the first function indicated by this first tick mark here, this first slash, is x1 of t, y1 of t. And then if I had a second parametric function, it'll be x2 of t, y2 of t, and so on. So here, x of variable is going to be cos variable. And y is going to be 4 sine of my variable squared. Let me go to my window. We'll let t go from, so about 0 to 4 pi. T step of 0.1 is probably fine. I expect my x min and x max actually to be -1 and +1. So I usually like a little bit of buffer on either side. So maybe I'll do -1.5 to +1.5. Oh, don't have my num lock on. There we go, +1.5. And then y I expect to go from 0 to 4. So I'll keep my y min, let's say, at -1, and my y max up at, say, 5. And if I just leave this curve kind of this way, if I just leave it as the setting is just drawing the curve, I'm not going to really be able to tell if I'm traversing it back and forth or not, because it's just going to be drawing over the curve that's already drawn. Since I want to see that behavior, I want to make sure that I've got that idea right. Again, I'm going to switch it to this option where it draws a curve, but it also has that bubble that kind of traces it out. So I expect the bubble to trace it out once from right to left, and then the curve will be there. But then I expect the bubble to go back and forth 3 more times. Okay, so let's graph it now and see if that happens. So we start on the right, we trace out to the left, that looks good. And we do get this bouncing back and forth now, as we expected. We should get one more. And there we go. So that looks like it's in line with what we expected. We're probably pretty confident now that we understand what's going on here. We have some anchor points. We kind of understand what the behavior is. So this looks like a quadratic, but it really only looks like a piece of a quadratic. It's only a piece of a quadratic that's traced out over here. And it's being traced out many times. Again, this is going to be very important, things like how many times do we trace something out? if we talk about, say, arc length or areas or some things like that. We'll want to know if we're tracing something out fully or if we're tracing it out more than once. That can cause some problems. Okay, so the next topic that I want to introduce is the idea of arc length. We're not going to spend a ton of time on arc length, but we'll talk about it and go through an example. If we have a curve C defined parametrically for t in alpha to beta, if f prime and g prime are continuous on alpha to beta, and importantly, if the curve is traversed exactly once, right? So up here in this example, we would have to be careful not to use, say, theta in 0 to 2 pi, which might be kind of the tempting approach, because that actually traverses the curve twice. It goes once from the right to the left and then again left to right. So our initial guess might be theta in 0 to 2 pi, but we see that that traverses it twice. We'd actually want to use theta from, say, 0 to pi, or from pi to 2 pi or something like that would be okay also. But we wouldn't want to go from 0 to 2 pi. So again, if the curve is traversed exactly once, and all the other things are true, then we can define the arc length of the curve as follows. You'll note that this arc length formula might look a little different from the end result of the previous arc length formula, but it's actually completely in line with the kind of intermediate result before we got to the square root of 1 plus f prime squared stuff. And it really comes from the same picture over here, that we have a horizontal deviation dx dt, we have a vertical deviation dy dt, and then for small deviations, for infinitesimal deviations, we can say that the arc length is just the length of the hypotenuse in the limit, and that's going to be root dx dt squared plus dy dt squared. How do we find the whole arc length? We integrate ds dt dt. So that's what we're doing over here. Okay, so let's work on this problem where we're going to find the arc length of a single arch of a cycloid. So we did graph the cycloid last time. So here we're looking for a single arch. We saw that the cycloid looked like this. And then it repeated itself after that. This was for theta equals 0. And then this was theta equals 2 pi. When theta equals 0, our y of theta is r times 1 minus 1. And when theta equals 2 pi, we also get that 1 minus 1. And in the middle, when theta equals pi, y is going to be r times 1 minus a negative 1, or 2r. So let's find the length of one arch of the cycloid. So when we integrate 0 to 2 pi, that will traverse this arch exactly once. And we want the square root of x prime squared plus y prime squared. By prime here, I mean d by dt, and under the square root, and then dt. So x prime of, or I should say d by d theta. X prime of theta is, well, r theta differentiates to r, and then minus r sine theta differentiates to minus r cos theta. Y prime of theta, the r times 1 differentiates away. Negative cos theta differentiates to positive sine theta. So y prime is r sine theta. And what is my integral? X prime squared is r squared 1 minus cos theta squared. y prime squared is r squared sine squared theta, and this should be d theta. So this is the integral I need to do. It looks a little scary at first, but the first thing we might notice is we can square this out, and we're going to get some cos squared thetas and sine squared thetas. That's maybe going to help us out a little bit. So let's do that first. I also noticed that everything has a factor of r squared. Let me just pull that r in front of the integral. So 1 minus cos theta all squared gives me a 1 minus 2 cos theta plus cos squared theta, and then plus sine squared theta from that second term. I note that this makes a 1, added to this one makes a 2. And then I have a factor of 2 in everything that can come out. Okay, so I've gotten myself to here. Oh, I need a little more room. So now what do I do with this 1 minus cos of theta? Well, here we can remember our double angle / half angle formulas, and we can apply one of those to get that so sine squared of theta over 2 is going to be 1/2 times 1 minus cos of theta. So 2 sine squared of theta over 2 is going to be 1 minus cos theta and d theta. So just applying one of our previous integration formulas, we see we get another square root of 2 that hits this one, makes a 2, integral 0 to 2 pi. We didn't do any substitution here. We just used the basic trig identity. So no changes to our variables or bounds or anything like that. Square root of sine squared just gives us sine of theta over 2 d theta. Oh, and I have an r here as well. So integrating this sine, that's going to give me a negative cos of theta over 2. If I differentiate that, negative cos of stuff differentiates to positive sine of stuff, but then I would get a 1/2 out, so I need another factor of 2. So I have 4r times negative cos of theta over 2 from 0 to 2 pi. So that's negative 4r times. And what do I get? I pulled the negative out, so I get cos of pi minus cos of 0. Cos of pi is -1. Cos of 0 is 1. That's being subtracted off. So I get a -2 times -4r is plus 8r. We can ask, does this kind of seem reasonable? And I think we can maybe say that it does. It's going, if we imagined a longer path, we would have to go up 2r, go down 2r, and then traverse 2 pi. So it would be kind of like 4r plus 2 pi would be a longer path. I think it kind of seems reasonable. I suppose we could, so we know that it's got to be bigger than 4r. We might, if we really wanted to double check things, we might take some kind of shorter path like this and make sure that was smaller, but I think that might be a little overkill. That's quite a bit of work just to do kind of a double check. kind of thing. We would see we'd have a, one side of our triangle with length pi, another side with length 2r. So we'd have 4r squared plus pi squared, square root of that, and then double that. So that might be quite a bit of analysis and thought, but this seems at least like a plausible answer. It's not like we got an answer like 100r or something like that that would seem, crazy. We didn't get a negative number. So this seems like it's in the realm of reasonable answers. So we're probably happy with this. Okay, so let's look at kind of an interesting application. The application of cubic Bezier curves. These Bezier curves are curves that are that have what are called control points. And these control points kind of let you draw a curve that's really nice and smooth and can get a lot of different behaviors. So these kinds of ideas, these Bezier curves or splines or similar ideas, are used in a lot of design work. So you actually see, like, Photoshop and things like that have a Bezier curve tool. So they're used in things like designs of cars, designs of ships, things like that. So if I want a smooth transition between 2 points, and I want to be able to control the kind of shape of that transition, that might be what a Bezier curve does. So the cubic Bezier curve is defined this way. It's a parametric equation with t as the parameter. It has control points, point 0, x naught, y naught, point 1, x1, y1, point 2, x2, y2, and point 3, x3, y3. So 4 points in the 2D Cartesian plane. These aren't necessarily points on the line. These are just the control points. Now, something that we might note is that our Bezier curve at t equals 0, well, when t is 0, my last 3 terms all have a factor of t, so they all go away. My first terms have this factor of 1 minus t cubed, and that's the only time t shows up, but plug in t equals 0, that all just becomes a 1. So my Bezier curve at t equals 0 is actually p0. So p0 does actually appear on the curve. It's the kind of start of the curve, so to speak. Similarly, my Bezier curve at t equals 1, now anything with a 1 minus t goes away, and I'm left just with these last terms here. The 1 cubed goes away, and I just get x cubed, or sorry, x3, y3. Or point 3, that control point is also on the Bezier curve, and it's kind of at the end. So typically we think of traversing this curve for t's in 0 to 1. So we move from control point p0 to control point p3. We might also ask then, okay, well, our points 1 and 2 on the curve, what is their function here? So let's take a look at that. So let's figure out first, what is dx dt? Let's find the derivative of dx dt and dy dt, and see if that gives us maybe some insight into where P1 and P2 come into play. So dx dt. Okay, for my first term, you get an x naught, and I get 3, 1 minus t squared times -1. For my second, I have a product rule. So I differentiate the first, I get 3x1, 1 minus t squared, plus from differentiating the second, I get 3 times 2 is 6x1. I get a t. I get a 1 minus t to the first power, and I get a minus 1. So if I did all of that right, differentiating the first, I just get 3x1, 1 minus t squared. That looks right. Differentiating the second, I get a 3x1t. The 2 hits the 3. I get a 1 minus t to the first and a negative 1. That looks correct. My third term is going to look somewhat similar. Differentiating the first, I get 6x2t, 1 minus t. Differentiating the second factor in that third term gives me a 3x squared, or 3x2t squared times a minus 1. And then our last term, 3x3 t squared, no product rule there. dy dt, of course, is very similar, right? Just replace here x0, x1, x2, x3 with the equivalent y's, and you get the same formula, just with those x's replaced with y's. So we might ask a question like, what is dy dx? Well, that's going to be kind of a pain to write out, but let's take kind of a hint from up here. We saw that when we plug in 0 or 1, a whole bunch of stuff goes away. So what's dy dx maybe at t equals 0? So we know the initial point. What's the initial direction that our curve is heading from that initial point? Maybe we can ask something like this. Maybe this is informative. Well, this is dy dt at t equals 0 over dx dt at t equals 0. Well, I know dx dt at t equals 0. All right, where are all the t terms? This one has a t, this one has a t, this one and this one do. So those are all going to drop off. These first two terms only have factors of 1 minus t. They don't have any lone factors of t, so they stick around. When I plug in t equals 0, those 1 minus t's just become 1s. So I'm left with 3x1 minus 3x0. And that is for the x's. That's on the bottom. The y's, of course, are going to be exactly the same, just with y's. I see my 3's go away. And what is y1 minus y0 over x1 minus x0? That is just the slope. I'll call it m01. It's the slope of the line from point 0 to point 1. The slope connecting those two lines. So this is really what point 1 does. Point 0 is our kind of anchor initially at time 0. And we leave p0, point 0, in the direction of point 1. And as an exercise, show that dy dx at t equals 1. So on the other side is m23. It's the slope of the line attaching point or connecting point 2 to point 3. So we end up at point 3 from the direction of the point 2. So let's investigate these a little further. You can Google Desmos Bezier curve, and you can come up with this utility that's pre-made by Desmos. And we can see our 4 control points here. We have P0 and P3 that are the initial point and final point of the curve. We have P2 we can see we leave P naught in the direction of P2, whichever way I kind of move this, I maintain that initial direction. And we approach P3, our final point, from the direction of my second point P2 here. Now you might say to yourself, okay, well, I can draw things like that basically look like quadratics, but there's actually a lot of versatility in these. You can say flip-flop these and get things that look kind of like cubics, you know, nice smooth transitions like this. You could do something like this, and you can get loop-to-loop kind of, you know, things. You can actually connect together several Bezier curves that, you know, maybe is a topic that's a little beyond the scope of this course, but you can connect them together in such a way that the transitions are nice and smooth and, you know, continuous differentiable transitions. And you can connect together a bunch of Bezier curves and, you know, come up with like a contour for a car fender or something like that, that maybe, you know, looks nice or has nice aerodynamic properties, those kind of things. And you see that you can get, you know, you can get very quickly a very good idea of what this curve is going to look like for different control points. It's very numerically efficient, and has a lot of freedom, right? So something we might be interested in is, well, I see that I can get one loop. Could I get like 2 loops or 3 loops? Is there, you know, I mean, I might play around a while and not be able to figure out a way to do it, but maybe is there a way to get more than one loop? So an interesting question that we could ask is, well, what does it mean? What does it mean in terms of my derivatives when I have a loop? Well, I can see that a loop has to have, or a loop will have between horizontal and vertical derivatives 3 of them, right? So in this case, I have 2 verticals and 1 horizontal. I could maybe have another loop, maybe, I don't know, something like this. I'm trying to come up with one that has 4. So maybe something like this has 4 derivatives, you know, 2 horizontals, 2 verticals. And I see that I could get 2 horizontal derivatives by setting dx dt equals 0. And I could, for some x choices of x0, x1, x2, x3, this quadratic could have 2 solutions. It could have 0 solutions or 1 solution, but it could have 2 solutions. Same with the y dt, it could have 2 solutions. But a quadratic equation cannot have more than 2 solutions. I cannot have 3 or 4 solutions. If I wanted to have, say, 2 loop-to-loops, if I wanted to loop once and then loop again, I'd have to have either, you know, 3 or 4 vertical tangents, or, you know, more than 2 horizontal tangents or something like that. And I can pretty readily see that that's going to break the algebraic side of things. So I can use the algebra side of things to get some intuition into the geometry. And I could have used the geometry, if I had started here, to get some intuition into the algebraic side of things and say, okay, it looks like I start at P0, end at P3, and it looks like I leave P0 in the direction of P1, and I approach P3 in the direction of P2. So maybe I would realize that kind of playing around with this, and I might, you know, in a different setting, have used the geometry to lend some information and expectation to the algebra. Wikipedia also has a pretty nice page on Bezier curves. So this is just the general Bezier curve Wikipedia page. And there's a little more depth to Bezier curves than, or a lot more depth than what we've discussed so far. But really what a Bezier curve is it's a linear, it's kind of a linear combination of these different points, whereas t goes from 0 to 1, we adjust the amount of influence each point has on the overall XY point. So we have our control points, 0, 1, 2, 3, and each of them for a given t has a certain amount of influence on the point XY. And as t progresses from 0 to 1, we see that when t is near 0, these latter points have very little influence because they're being multiplied by a small number. When t is, say, a moderate number, these middle ones have a lot more influence, and when t is a large number, when it's, say, near 1, t cubed is going to be a lot bigger than, say, 1 minus t cubed. So then the third point will have a lot of the influence. So if we think of that we're just kind of, trading off weighting between one point and the next, we can think of a, say, linear Bezier curve as just being the line that connects P0 to P1. This would have two control points, P0 and P1, and it's just starts at P0, goes to P1 in a nice smooth line. A quadratic Bezier curve, which would have three control points, it would look like x naught times 1 minus t squared plus 2x1 t1 minus t plus x2 t squared. We can see that it has these three control points. We leave P naught in the direction of P1. We approach P2 from the direction of P1. And in between, we really can actually build up a quadratic curve from linear curves. We can think we have a linear curve, this green one here. Let me zoom in a little bit. This green curve here, acting like a Bezier curve. We start at the leftmost point of the green line, and we progress to the rightmost point. Meanwhile, the left point of the green line progresses from P0 to P1, and the right point of the green line progresses from P1 to P2. So we kind of see that borne out over here. So our left end point of our green line progresses from P0 to P1. Our right end point of the green line progresses from P1 to P2. And the point XY is gotten by progressing from the left end point of the green line to the right end point of the green line in that linear fashion from above. And then the cubic Bezier curve just does kind of the same thing, but just with more lines, right? We have our left green line goes from P0 to P1. Its left endpoint goes from P0 to P1. Right endpoint goes from P1 to P2. The right green line, its left endpoint goes from P1 to P2, and right from P2 to P3. The blue line, its left endpoint goes along the left green line from its first point to its second. The right endpoint of the blue line goes along the right green line. And then the actual curve XY is traced out by progressing from the left endpoint of the blue line to the right endpoint of the blue line. So it gets progressively more difficult to explain and to see what's going on for the higher level curves. But I think the quadratic is the really nice one. I think the quadratic really captures all of the complexity without too many moving pieces. And then you can see they even have animations of higher order curves. Typically, I think one would stop at a cubic, and then if you need more nuance, more interesting features, you would piece together cubic Bezier curves instead of going to higher order, fourth or fifth or something order curves. The numerics, what you're asking of the computer just becomes much more difficult when you go to higher order. So it's a much better problem to try to solve from the computer side of things, to put a bunch of cubics together, than to try to do a 10th order Bezier curve or something like that. It's going to be much easier for your computer to handle a bunch of cubic Bezier curves than a single really complex Bezier curve. Okay. So let's look at this this next example then. So another application of parametric equations. So here our goal is to find a parametric function to describe the involute of a circle, which we're going to explain what that means. And we'll also try to find all of the horizontal and vertical tangents on 0 to 2 pi. So what is the involute of a circle? So let's say we have a circle like this. And let's say that we're thinking of a certain angle along that circle. And we can imagine that we have kind of taken a rope, maybe say around like a telephone pole or something. We've wrapped it around that telephone pole tightly a bunch of times. And then we keep the rope taut and start unwinding the rope. So if I have my rope here, the end of it that it's been wrapped around clockwise, and I'm going to start unwrapping it counterclockwise, but I'm going to keep the rope taut. So as I walk around the pole, I'm going to have a length of rope that I have pulled away from the, let me draw that a little better. Have a length of, as I walk around this way, I'm going to have a length of rope that I have pulled away from the pole. The further I walk around the pole, the longer that length of rope is going to be, right? So the involute of a circle is the path that I will trace out as I walk around this pole, keeping that rope tight, noting that as the further I walk around the pole, the longer the rope is, the further away from the pole that I will get. So that's what we mean by the involute of a circle. So let's draw this a little bigger and a little nicer. So I'm going to just kind of focus on the first quadrant here. I guess I can get rid of a little bit of those. I'm going to focus on the first quadrant here. I have my origin. I have my angle. And I have my bit of rope here. So in other words, at some point when I'm starting to walk around the pole, keeping this rope taut, where the rope will lose contact with the pole is at angle theta. That will be, I note that my rope is going to be tangential to the circle there. And I know that my radius is always perpendicular to the tangent line to the circle. If you're not sure of that, that's a pretty common Calc 1 example in implicit differentiation. So that would be a good exercise for implicit differentiation, show that those two are perpendicular. So we know that that's a 90-degree angle there. I have this point, let me just call this point T for the point of tangency. Let me call this point P for the point that's the XY point that we're concerned with for our curve. This is going to be the XY relation that we're interested in that will trace out our curve. And we think that this is going to be a function of theta. So the more rope that I unwind, the further theta progresses, the further that point of tangency goes around the pole, and then XY will progress in a certain way as theta progresses. So we can imagine having two different triangles here. I have a triangle that goes from the origin to this point on the x-axis to the point of tangency. And I have another triangle that, maybe I'll do this one in a different color. That goes from my point P that I'm interested in to the point of tangency and then makes a right triangle. And for kind of convenience, I'm going to flip this over. I'm actually going to draw this triangle this way. We're trying to draw these fairly nicely so that we can kind of keep track of how everything lines up. So this point is x comma y. This origin is 0, 0. Okay. I know that this, I suppose I don't know that because I didn't label it yet, but my circle has radius r. So I know that this hypotenuse here is angle r, or distance r, and this angle is angle theta. Okay, so I know for this triangle, I know that for, say, my opposite side, I know that sine theta is opposite over r, or this opposite side is r sine theta. And for my adjacent side, I know that that's r cos theta for the same reason. Okay, so the blue triangle, not super difficult. For the red triangle, okay, what do we know here? I really want to find a side length and an angle. Okay, so it seems like my best shot for a side length would be this T to P distance here. I know that the distance T to P, well, that's just the arc length of this chunk of the circle, right? That's that circular segment. It's a circular segment. I mean, I've straightened it out into a line, but it's a circular segment of a circle of radius r over angle theta. So it has distance r theta, thinking of theta in radians. Okay, so that's just that length of that circular arc, r theta. I also know that my angle theta, if I flip these angles around a little bit, and so on, my angle theta is going to be that angle P. So now what do I have over here? Similar to the blue triangle, I have this, the side next to the T, the opposite side from theta is going to be r theta, the hypotenuse, sine theta. And my side adjacent to theta, the side near P, is going to be r theta, the hypotenuse, cos theta. Okay, so then what is x going to be? Well, x is going to be my blue horizontal distance, r cos theta. That gets me out a little ways, but then I have to keep going. I have to keep going this additional distance to get to P. So plus, what's my horizontal contribution from the red triangle? R theta sine theta. So for a given theta, this is what x will be. And for a given theta, what is y? So I note that my height up to T, the point of tangency, is r sine theta. But then I note that I'm going in the opposite direction. I went up to the point of tangency, and I'm going down from the point of tangency to the point P. So I have a minus r theta cos theta. This is why I wanted to draw this kind of carefully so that we could keep track of, that in the x direction things are adding together, but in the y direction they're kind of opposing each other. So these are our parametric equations. So we found the parametric function. And now let's find the tangents. dx d theta is negative r sine theta plus r sine theta, differentiating the first, and then plus r theta cos theta. These guys go away, and this is just r theta cos theta. So when do I get a horizontal tangent? When is this 0? Well, this would be if theta is 0, or if cos theta is 0, pi over 2, 3 pi over 2. These are at least potential horizontal tangents. We got to be a little bit more careful, which we'll talk about in just a minute, but let's get dy d theta. So what's dy d theta? That's going to be r cos theta minus r cos theta, differentiating the first, and then plus r theta sine theta. These bits go away, so I'm left with r theta sine theta. And I ask, when is this 0? And my candidates here for vertical tangents are when theta is 0, or when sine theta is 0, which is 0 or pi. So I note that I have a vertical tangent if dy d theta is 0. Or sorry, I have a horizontal tangent if dy d theta is 0, but dx d theta is non-zero. So I have a horizontal tangent at theta equals pi. That's kind of undisputed, right? I don't see a pi up in these solutions. I have a vertical tangent if dx d theta is 0 and dy d theta is non-zero. So I have vertical tangents at pi over 2 and 3 pi over 2. Those are also undisputed. Does this kind of make sense from the figure that we would kind of expect to get something like this? Yeah, we'd expect to get these I think I did say oh. All right, sorry about that quick interruption. Anyway, what I was saying was for dx d theta, when it is 0, we get, and when dy d theta is non-zero, we get I think I wrote these just backwards. Okay, so we should get vertical tangents when theta is pi over 2 or 3 pi over 2. And we should get a horizontal tangent at when theta is pi. Those are the undisputed points here. We get dx d theta is 0 at pi over 2 or 3 pi over 2, and dy d theta is non-zero there, and then vice versa for theta equals pi. So we note that if we look up here at this picture, when, say, we're at theta equals pi over 2, we can kind of envision that as being maybe this point where we get a vertical tangent. When we make it over to theta equals pi, we've unwrapped more of our cord at this point, our rope at this point, we could envision that as maybe being a maximum before we start, a maximum in the y direction before we start coming back down in the y direction, and so on. So those are our kind of clear points of tangency. But then we have an interesting case when theta equals 0. So what do we do when theta equals 0? So here we look back at, what do I mean by horizontal or vertical tangent? I'm interested in dy dx. Or dy dt over dx dt. Now at theta equals 0, this equals 0 over 0. Right, and I, of course, mean d theta here. My dy d theta and dx d theta are both 0 at theta equals 0, so I have an indeterminate form. So what do I do here? Well, I would take the limit of dy dx, dy dx as theta goes to 0 from above, and I would see what that is. So what's the dy dx? It is going to be r theta sine theta over r theta cos theta, or it's going to be tan theta. And as theta goes to 0 from above, I see that dy dx is going to go to 0, or a horizontal tangent. So I see I also have a horizontal tangent at theta equals 0. Okay. So the last thing that I want to talk about is polar coordinates and polar curves. And so again, we introduced this idea in the last class lecture. So we'll just kind of pick up where we left off. We had derived the relationships between x, y, and r comma theta. And now we want to do this kind of slightly more confusing, more challenging conversion, converting x, y equals -2, -1 into polar coordinates. So x, y, -2, -1, I see that's in the third quadrant. So I'm looking for theta and r. In particular, I'm looking for a positive r, and I see that theta is going to be between 180 and 270 degrees, or pi and 3 pi over 2. Now, what can kind of make this challenging is that I have tan theta is pi over x is -1 over -2 is 1/2. If I arctan 1/2, that actually gives me the same angle as if I was converting +2, +1 into polars, right? Because these negatives cancel. Another way to look at it is we have the periodicity of the tangent function. The kind of middle piece of the tangent function goes from -pi/2 to +pi/2, but then we have a separate copy that goes from pi/2 to 3 pi/2 and so on. So that right, that can cause a little bit of confusion if we're not being careful with the geometry. So I'll take a theta hat, I'll call it is arctan of 1/2. So that's going to be an angle but it may or may not be the ultimate angle that I'm looking for. So if I do arctan of 0.5, and again, making sure in my mode that I'm in radians, and I am, I see that gives me about 0.46 radians. Well, we know that pi is, say, about 3, and 3/2 of that is, something like 5. This is certainly not in the interval that we're expecting. This would be the equivalent first quadrant angle for, say, +2, +1. How do I get the third quadrant angle that I'm after? Well, I note that this angle theta hat really kind of goes here on the bottom of the x-axis. So really we need theta is pi plus theta hat, or about, we add pi, and we get about 3.61 radians. And then r is always easy to compute. It's just square root of 2 squared is 4, plus 1 squared is 1. So square root of 5 gives me about 2.24. So the point x comma y equals -2, -1 is equivalent to r comma theta equals 2.24 comma 3.61 radians. Again, it's easy to just mistakenly do arctan and then just run with that answer. But again, we typically want our theta to be between 0 and 2 pi. So if the arctan gives us maybe a negative angle as the answer, we'd want to add, we'd want to add, well, we'd want to make the change to make our trig work out properly. So if it gives us a negative angle, say something like this, we may have to add pi if we were originally looking for a third quadrant solution, or if we were looking, for a second quadrant solution, or if we were looking for a fourth quadrant solution, we'd have to add 2 pi. So we may get an answer that's theta hat itself. We may have to add pi to theta hat. We may have to add 2 pi to theta hat. I think probably trying to think through all of the different possibilities and come up with an algorithmic approach is kind of cumbersome. I think it's much easier to draw the picture, decide where you want, what quadrant you want your solution in, and then kind of work out how you can take the answer that you get from the arctan and rotate it around to the proper quadrant that you need. If you need to at all. If it's a first quadrant point in the Cartesian plane, then just doing the arctan will get you the answer without any problems. Okay, and then the last thing that I want to talk about are these polar curves. So we understand now that we could talk about the Cartesian plane in XY coordinates, and then we could have a function y in terms of x that says what are the allowable xy coordinates for this relation. But we could also have, think about this two-dimensional plane in terms of polar coordinates, and then we could ask, what are the constraints in the polar world, r versus theta? What are the constraints? What are the constraints on the allowable points in the plane that satisfy this equation? Okay, so let's first look at the kind of simple, in a sense, polar curves. So theta equals 2. if I think of a relationship theta comma r, where I have, say, some inputs theta and some outputs r, this is saying that whatever value of r that I'm interested in, whatever point that I'm interested in, it satisfies this equation if and only if theta is 2. So what does that mean? Theta is the angle, so that's saying that I start looking along the x-axis, I rotate counterclockwise 2 radians. So pi going all the way around to the negative x-axis is roughly 3 radians. Pi over 2 is like 1.5. So I'm somewhere in the second quadrant here. I'm looking in this direction. So what pairs r comma theta satisfy this? It can really be anything, comma 2. So I could point in this direction and go out 1 unit or 2 or 3 units. I could go 0 units. Now, also, whenever we get to polar curves, we're going to allow for negative r's as well. So I could go pointing in this direction. I could go -1 units in that direction, or kind of walk backwards into the fourth quadrant 1 unit, or 2 units, or 3 units. So in a polar curve, this kind of a, what you might call, say, a degenerate equation, these would be like vertical lines in the xy world. These kind of degenerate equations where we just have theta equals number, these represent straight lines in the xy world. So what about r equals 2? Another special case. We know that when we have, say, y equals number in the xy world, those are horizontal lines. So what about r equals 2? Well, here we're saying what points r comma theta are admissible here. Any point that has a radius of 2, regardless of what its angle is. Or if I have whatever input theta, as long as the radius is 2, that's an admissible point. That's a point that satisfies r equals 2. So this was A. So for B, the picture is going to look like, if I am at angle 0 pointing along the x-axis, I go 2 units out. If I'm at an angle pointing this way, I go 2 units out. Pointing vertically, I go 2 units out. I just sweep out this curve of constant radius 2. And I note that r equals 2 is a circle with radius 2. So the constant function in the polar world is what we would call a circle in the xy world. It's the function that has constant radius, constant distance from the origin. So what about graph C? R equals sine of theta. So let's think about some different points here. Well, when theta is 0, sine of 0 is 0, so r is 0. When theta is pi, we're back to 0. And when theta is 2 pi, we're back to 0. When theta is pi over 2, sine pi over 2 is 1, and sine of 3 pi over 2 is -1. So let's just see if we can get a general idea of what's going on here. So when theta is 0, I'm pointing along the x-axis. I go 0 units in that direction. So I start at the origin. As theta progresses up to pi over 2, I increase in size from 0 to 1. So when I'm pointing a little bit counterclockwise of the x-axis, I'm a little bit positive. When I'm a little more clockwise, I'm a little more positive. And then I make my way up to 1 here. So I get something like this. So that's at pi over 2 comma 1. But now what happens to sine as we go from pi over 2 to pi? It decreases from 1 back down to 0. So as I'm working my way around to look along the negative x-axis, my radius is going from 1 back to 0. So I've made my way back to the origin here. So I've traversed this loop, this circle, 1 time over here. Now what happens on the next bit? So now I'm looking along pi, I'm looking this direction, I'm looking along the negative x-axis, and I go 0 units in that direction, so I'm sitting at the origin. As I go from pi to 3 pi over 2, sine starts becoming negative and goes from 0 to -1. So as I'm rotating this direction, when I'm a little further that direction, I'm going a little bit negative. When I'm a little further that direction, I'm going a little more negative. I'm actually tracing out the same curve. And when I get to 3 pi over 2, I'm at -1. So I'm tracing out the same curve a second time. And then similarly through the 4th quadrant. So I expect to get this circle in the kind of positive, in the positive half plane, in the top half plane. I'm expecting to traverse it twice from 0 to 2 pi. Let's see if we can replicate that on the calculator. So right now I'm in parametric mode, but if I come to my mode and I have my function mode, my usual y of x mode, my parametric equation mode, and the next one over is polar. So if I go to polar, and again, I'll make sure I'm in radians. Now if I go to y equals, I see I have R1, R2, R3, etc. These are R of thetas. I'm going to do my same trick as before. I'm going to change my plot type so that it has that bubble that kind of follows along, because I expect that bubble to trace out the circle once and then to follow it again a second time. And then I want sine of my variable, which is now a theta. If I go to my window, I'm going to pick theta from 0 to 2 pi. And that seems like a reasonable step. My x min and x max, let's leave those at -1.5 and 1.5. That seems reasonable. My y min and y max, I think y is going to be positive everywhere, so let me keep y min at -1. That's good. That should be able to confirm that it doesn't dip negative. And y max, I think, is going to be 1. So let's make the y max of the window 2. I think the maximum is going to be 1, but this will give me a little bit of buffer. And I'll graph it. And I see I've traced it out, and I've traced it out a second time. If I wanted to, I could go to zoom and then zoom square 5. What that'll do is square up the window for me so that I can actually see that this is actually a circle that it's drawn out. So we could go through the same kind of argument for D and E. We could think quite a lot about it. Let's though leverage the calculator for these two. So let me look at 3 sine of theta and graph that. So as I might expect, this just a circle in this upper half plane that's just 3 times as large, right? We're going from 0 to 3 to 0 to -3 to 0. Everything is just scaled up by a factor of 3. So if I wanted to take my window from, say, a y of -1 to, oh, I don't know, maybe +4, and graph it. And then maybe zoom square. And I see it's just a scaled up circle. But what about sine of 3 theta? So instead of putting the multiplier on the outside, what if I multiply the inside? What if I multiply the independent variable basically instead of the dependent variable? So if I do sine of 3 theta, I know that my radius now is going to be stuck on -1 to 1 without question, right? So let me change my x min and x max to -1 and 1. And same with y min and y max, -1 to 1. And again, we'll graph this. We'll go from 0 to 2 pi. So now we get a very different looking curve. And again, we see that we actually traverse that curve twice. Let's zoom square. Since these are kind of new curves, this lets us get a better perspective on them. So I have this kind of flower with 3 petals, and I'm traversing it twice. I start at 0, 0, and then I traverse the first petal, the second petal, halfway by the time I get to pi over 2. From pi over 2 to pi, it takes me the second half of the bottom petal and the entire top left petal. And then from theta going from pi to 2 pi, that's whenever this, that's whenever we're going to traverse this a second time. So from pi to 2 pi, sine is going to be negative for a bit, then turn positive. It's going to be negative for a bit here, then turn positive, and then turn negative again back to 0. So what if I tried something like sine of, say, 5 theta? So a flower with 5 petals. Okay. So the number in front of theta kind of relates to how many petals that we have. What if I do, say, sine of 4 theta? So here I get something interesting. On the odd multiples of theta, I trace out the curve, and then I trace out again on the second half. For the even multiples of theta, I trace out a curve, and then I trace out kind of a mirror image, but it turns out that it doesn't exactly overlap the previous bit. So I still get a lot of symmetry from that second half, but in a slightly different way. So a lot of interesting things you can get from these polar curves. This is just kind of an example, a list of some examples of some phenomena you can see. So we can use the calculator as a tool for exploration, or we could use, we could use this kind of more basic understanding and think through it, either plot points or something similar to that. So I think ideally you kind of use both, right? You use your mind, you use what you know about things to come up with something that you might expect. You see it borne out on the calculator, and maybe the calculator gives you a little more insight when you actually see the picture and you recognize, like, oh, this thing that kind of looks circular, but I wasn't sure if it was a circular, and the calculator really looks like a circle. So I'm pretty sure it's a circle. And then maybe you come back to the, calculus world and try to maybe prove that it's a circle or something like that. So really, using both, going back and forth, using them hand in hand, I think is the best approach. Okay, so that was what I had for today for the supplement. So I will I'll end the supplemental video, and then when we come back in class, we'll continue on with chapter 10, talking about things like areas and polar curves, maybe a little bit more in polar curves, a little bit more in basic polar curves, areas and polar curves, and then move on.